Okay, so hi everyone, I am Shivani Dhok and today I'll be covering week 3 tutorial, week 3 content. So, yeah, to begin with, I'll just recap whatever was covered in week 3. So, in week 3, the first thing that was covered was differential equation representation of LTI systems. In that, linearity and time invariance conditions were also discussed, followed by then discrete time LTI systems were discussed, and for this the convolution sum, that is output and input output relationship, was again based on convolution, which was given by this form. That is, if y of n is my output, then the output is given as summation for k running from minus infinity to infinity x of k h of n minus k. This is very similar to what you get for your continuous case, which was for this was for discrete. So for continuous you are having something like this, x of tau h of t minus tau d tau. So it is almost a similar case, just here you were having integration and now you will be having summation in discrete case. Same conditions of memorylessness, causality and stability were there. That is, for a memoryless system, my impulse response h of n was of the form a delta n, where this delta n is my discrete time unit impulse. Then for causality, so this was for memoryless. Then for causality, h of n was equal to 0 for all n which are less than 0. So if this is satisfied, then it is a causal system. And again, difference equation representation was also covered. So for continuous time, it was differential equation, that is, it was of something this form. Where this k is running from 0 to m, and there is some coefficient, let's say alpha k, which is equal to summation k running from 0 to n beta k dk by dk xt by dt. But for discrete time systems, this gets converted to your difference equation representation, and that is of the form of summation k running from minus infinity to infinity alpha k y of n minus k, which is sorry, not in 0 to m, which is equal to summation k running from 0 to n beta k x of n minus k. This was a difference equation representation. And the third thing that was introduced in this week was Laplace transform. I'll look at this Laplace transform, its definition at the end. I have 2 questions for this Laplace transform. In that, I'll try to cover its concept as much as possible so that you can have some solving in week 3 or week 4's assignment. So I'll try to cover this Laplace transform concept more properly. So before that, let us start with the question, the first question. And here I am giving a glimpse like how the convolution sum for discrete time systems is derived. Like in the lecture for convolution of or for input output relation of this continuous time system was properly derived in the lectures, but we'll try to see how we get this summation using the same concepts that were used to derive this equation. So basically what we are having here is, we are having a discrete time system. Let's say it is given by t. Its input is x of n and its output is y of n. And we need to find what this y of n is. And what do you mean by an impulse response? An impulse response is the output which I get when my input is unit impulse. So when my x of n is unit impulse, the output that I get is known as my impulse response. So I'll represent this simply like this. So for the same system, if my input is unit impulse, then my output y of n is the response to this unit impulse and hence known as impulse response of the system. Now let us shift this input by some factor k. Let's delay it. Now since my system is LTI, we will use time invariance property and we'll have the shifted output, and the shift will be same as the shift in input. So this is time invariance. Then let us multiply this by x of k, and this will give me x of k h of n minus k. So here we are exploiting homogeneity property. So this is homogeneity. So x of k is constant, so it's okay. Now let us sum it up for all possible values of k. That is for k running from minus infinity to infinity, x of k del of n minus k this results in summation k running from minus infinity to infinity, x of k h of n minus k. Now if we look at this factor here, this factor is nothing but x of n. So if my x of n is something like this, 0, 1, 5, 2 and so on. So this is starting from, let's say, k equal to 0 and it's 0 otherwise. So let us say 0 for n less than 0. So this is basically my x of 0. This is my x of 1 and so on. So I can represent this as x of 0 into del of n plus x of 1 into del of n minus 1 and so on. So this summation, if I take this summation over all the possible values of k, that is if I represent it in this format which is given here, so this is basically giving me a representation for my input signal x of n. So if I am giving an input of x of n, the output that I am getting is of the form of this, that is summation k running from minus infinity to infinity, x of k h of n minus k, and this is my output, and this is known as convolution sum or convolution. Is this okay?
Yes, ma'am.
Oh. Let us look at the next question. So here we'll try to understand, we'll try to classify the systems when we are given the impulse response. We'll classify the discrete time systems based on causality and stability by observing its impulse response. So let us look at the first one. So this is my first system that I am considering whose impulse response is given as, so the first one is h of n is equal to 5 power minus n u of n minus 4, where this u is unit step. So let us try to sketch this first. So this is my n axis, this is my h of n. Now this u of n is basically starting from n equal to 4. So this is 0, 1, 2, 3, 4 and so on. So this u of n will be giving me value 1 when my n is greater than 4. That is, this argument n minus 4 should be greater than or equal to 0, which means that it is non-zero only when my n is greater than or equal to 4. That is, it will start from this point. And this u of n is getting multiplied by 5 to the power minus n. So at n equal to 4, this will be taking a value of 1 by 5 to the power 4. Similarly, this will be taking value of 1 by 5 to the power 5, that is at n equal to 5, and so on. Now if we observe this range and the negative range, we can clearly say that our h of n is equal to 0 for all n which are less than 0, which means that this is a causal system. Now let us look at stability. So a given system is stable, it is Bibo stable if my impulse response is absolutely summable. That is, the summation of n running from minus infinity to infinity mod of h of n is less than infinity, then my system is stable. So let us try to find this summation for our given impulse response. So this will be summation n running from minus infinity to infinity mod of 5 power minus n u of n minus 4. Now this is positive from n equal to 4, so this I can safely write as summation n running from 4 to infinity. And another thing is this 5 power minus n is always a positive quantity, so I can just simply write it as 5 power minus n. So this summation I can write as 1 by 5 power 4 plus 1 by 5 to the power 5 plus 1 by 5 power 6 and so on. So this is your simple infinite geometric progression, and therefore we can write it as the first term upon 1 minus the common ratio. So this comes out to be 1 upon 5 cube into 4, and this is less than infinity, which means that it is a stable system. Is this okay? Any questions at this point?
No, ma'am, clear.
Okay, thank you. Let us look at the second part of this question. Here my impulse response is given by the second part. My impulse response h of n is equal to 5 power minus n u of n plus 4. So we'll again sketch this first. So this u of 5 power n, this u of n plus 4 will be non-zero when my n plus 4 is greater than or equal to 0, that is my n is greater than or equal to minus 4. And at minus 4, this 5 power minus n will be taking value as 5 power 4. So the signal that I will be getting is something like this. So here I have 5 power 4, then I'll be having 5 cube, 5 square, 5, 1, and so on. Now if we observe this range, and before this it will be 0, that is at minus 5, and before it will be 0. So if we observe this range, so my h of n is not equal to 0 for some n, that is n equal to minus 4, minus 3, minus 2, minus 1, and therefore it is a non-causal system. So this system is a non-causal system. Now let us again look at the stability aspect. So for that, let us look at this. Summation n running from minus infinity to infinity mod of 5 power minus n u of n plus 4. So since this is non-zero from n equal to minus 4, I can safely write it as n equal to minus 4 to infinity. And this 5 power minus n is a positive quantity, so I can write it as 5 power minus n. And this is again an infinite geometric progression, which is something like this: 5 power 4 plus 5 cube plus 5 square and so on. So this comes out to be 5 power 4 upon 1 minus 1 by 5, which is equal to 5 to the power 5 by 4. Again, this is less than infinity, which means that this is a stable system. Let us look at its third part. If you have any questions in this, please stop me in the middle and you can ask at any point. If you have any questions in this part, please let me know. Okay, let's look at this third one. So this third one has an impulse response of h of n equal to 5 power minus n u of minus n minus 1. So if I sketch it, so this u of minus n minus 1 basically starts from this part, that is minus 1, and at minus 1 its value is 5 power minus 1, that is 1 by 5. So at minus 1 it has a value of 5. Then at 2, just give me a moment, minus n minus 1 should be greater than or equal to 0, that is n should be less than or equal to minus 1. Then at 2 it will be having a value of 5 square and so on. So now we can observe that this system is having non-zero values for all the values of n which are non-positive or which are negative. That is, I am having h of n to be equal to 0 for all n which are greater than or equal to 0, which means that this system is anti-causal.
Here, madam,
Yeah,
the, the value at minus 1, is it 5 or 1 by 5?
you substitute n equal to minus 1 here, sir.
Okay. Well,
Yeah,
minus becomes plus.
yes.
Okay, and that another clarity. See, how do you, how could you make out that it starts from minus 1, the
Oh,
series?
okay. Now you look at this factor here. This is u of n, and u of
Yeah.
n is minus 1 minus 1, this factor. It is non-zero only when my this argument is greater than or equal to 0, which means that my n, if I take this n to this side, is less than or equal to minus 1. So when this
Okay.
is satisfied, then only my series like this multiplication is possible.
Maybe actually mentally I'm following another model, like minus n minus 1 can be written as minus of n plus 1. Uh,
Okay.
okay, then yeah, you shift left and then invert
No, no,
here.
no, no, no. Here it's like this.
Yeah,
See, this is your U of n.
right.
Okay. Then what you are saying is, can you repeat what you were saying?
Yeah, what I was thinking is that that you shift left the sequence by
Like
one.
this.
Yes, yes, and then flip around, flip. minus, flip around y-axis. Is it the same?
Like this.
And then flip around y-axis. Yes. Is it different, right? Is it
Yes,
same?
it will be different. Now this
Oh,
is happening because you are first flipping, first you are shifting and then flipping. So what
uh,
you are doing is you are first doing this and then you are
yes,
flipping. So you are
yes.
doing this.
So which is the right one? Which is the right method? Mm, No, no. Yeah, yeah. So I need a simple technique to sketch this. The
Okay, you
sketch.
want to sketch like how you of n things happen and that kind of stuff.
Yeah, yeah,
Okay,
yeah.
1 minute. I'll do that. 1 second. No problem. I'll
Yeah,
add one
different
slide.
combinations of u minus 2 plus 1 minus n minus 3.
Yeah,
You know,
yeah. I understood what the problem is. You are not able to handle how that shift and flipping is happening when
right,
it is
right,
combined. Okay,
right.
okay.
Particularly during convolution, I'm getting confused. Okay.
Okay, okay. I got it. I got it. So I'll add one new slide here. So let us. So this is u of n. I'll start with very basic thing.
Yes.
This is your u of n, like this, and so on. So this is at.
In fact, it could be any signal. It could be x of n also. Need not be u of n. Yeah. It could be.
Okay, you give me any signal, like it will be easy for me to sketch
Yeah.
then.
Okay. Okay.
Shall I take something different? Because
Yeah.
u of n is very simple.
Yeah. You take x of n, some random signal, maybe right side signal. Okay.
Okay, let's take it very random signal. So this is
Or both side signal you take, which includes both.
okay. Okay, fine. So let's say we'll take a short signal. Let's say it starts from -2, -1, 0, 1, 2, 3, and so on. So let's say my signal is taking value of 2 here. Then it is taking a value of, yeah, it is taking a value of 1 here. Then it is taking a value of -1 here. Then again it is taking a value of 1, and it is taking a value of 1 again. This is okay?
Okay. Okay.
Yeah. I don't have anything for my reference, so I'm doing it here only. Okay, so first thing what we'll do is we'll shift it by some factor. So we'll do it like this, x of n minus 1. Okay.
Okay.
Now what you had was x of n, and now you're having this, that is x of n minus 1. So let me label this as x of like this argument n hat equal to n minus 1. Okay, so n equal to n hat plus 1. So what does this mean? Whatever was present earlier at n equal to, like, okay, whatever was present at 0, so this is n hat, right? This is
Right.
your n hat, and you're playing with n.
Right.
So whatever was initially present at 0 will now be available at n hat plus 1, that is 0 plus 1, that is 1.
Right. Right.
Right. So means you're shifting the entire signal towards right.
Right.
So what you will be getting is something like this. That is, you will have a magnitude of 2 here at -2, then 1 at 0, then it will be -1. Sorry, at 0 it has nothing. So it will be 0 here, then at 1, 0 here. Then again I'll get -1, 1, 2. Then
No,
I have,
no. The zero also. The original one zero also has a minus one.
no, 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 sorry. 1 second. This is black. This is just, I extended the axis.
So now the new one becomes minus one. Yes.
Sorry.
Now in the original one, at 0 also there is a -1, right?
No. At 0, it's 0.
Oh, 0 is 0. Okay. Right.
Hmm. And it's 4. At 4, I'll have again 1. This is okay?
Okay. So you're shifting the whole sequence, you're shifting by one step, right?
Yes.
One
Yes.
step right.
Yes.
So one step right. Okay.
If I have +1 here, then I'll shift it towards left.
Left. Now the issue is, -n+2, something like that.
Okay, you want x of -n plus 2, like this.
Yes.
Okay, so when you are given this factor, this you can solve it in two ways. I'll go step by step. So the first thing is this operation, that is x of n. It is shifted by 2 factor like this. That is shift
Shifted by 2.
by
Yeah.
2.
Yes.
That will be leftwards. Okay,
Right.
and after that I'll flip it. So this is minus of n plus 2. So when you're flipping now, at that time you won't put a minus sign to whole argument. You will put a minus sign only to n.
Okay.
Yes.
Okay. Okay. That means first you have to shift and then flip.
Yes. Now this thing I can also solve in this way. That is second thing. That is x of n. I'll write this x of minus n plus 2 like this. X of minus of n minus 2. Okay.
Okay.
So for this, what I'll do, x of n, I first flip it. So I'll
O-
get x of minus n. And
Okay.
now I'll shift it by minus 2.
Okay.
So this
Okay.
will be x of n minus 2. And anyway, when if you solve by some fashion and if you get confused in any fashion, any way, so what you have to do is just take this factor here, let it be n hat equal to minus n plus 2, and now your actually running variable is n, and I'm just replacing it as n hat. So what I'll do is I'll just make some changes. N equal to n hat minus n hat plus 2. Is it correct? Yeah. So whatever was present earlier at 0, that will be now available at 2. Like
Okay.
that you have to, like that kind of sanity check you can have
Okay.
whenever
Okay.
you are doing this flip and shift operations. So actually be a bit careful while doing these kind of operations. Means this shifting and flipping are actually not commutative operations. Like if you are shifting, so if I am having x of t and if I am doing this shift by a and then flip, or let's say scale by something, scale your time axis by b, you'll get some output. So what is happening is x of t plus a, and then you are doing this x of bt plus a.
Yes.
But if you do this x of t, you first scale by b and then shift by a, then here what you are doing bt, and then after that what you're getting is b of t plus a. You have to play with t, not entire argument. So this is actually x of bt plus ab, and these two signals are not same. So these
O-
operations what you are doing are not actually commutative. So you have
Okay.
to be very careful while doing these.
Okay. Okay. Yes. Yes. I got it. Yeah.
You got
Okay.
it. Now you look at this. What you had tried was this one. So you first shifted and then flipped. But what you had to do was you first have to flip it. and then shift it. See, see this one, this one. It is same thing, right? Second point here, this one. So you are having x of minus of n minus 2. So first you have to flip and then shift. So if you write it in this fashion, like if you bring your signal in this fashion, first you scale by a and then flip by then shift by b, or shift by minus b. So for me, what was easier thing was I used to just simplify it in this form. It is u of minus u of my sorry, I'll use this example, u of at minus ab. Then what I used to do was I used to first handle this shift, and after shifting I'll just scale by this factor a. I'll do the same thing with this now. What was given to me? U of minus, I'll do by both ways and you will get the same solution. I'll do by both ways. So the first way is u of minus n minus 1. So what I'll do is first I'll shift u of n by minus 1, that is I'll get u of n minus 1. So what will be that? It will start with 1. It will be like this and so on. So this is my u of n minus 1. This is okay. And after that I'll flip it. So then this 1 which was present at 1 will now be available at minus 1. So this is the signal that I'll get. So this is u of minus n minus 1. And the second way which you were proceeding was this, u of minus n plus 1. So what I'll do is I'll flip this u of n. So my u of n starts with 0. So I'll do it like this. It was first towards right, now it will be just flipped. So first I'll have u of minus n and so on. And now I'll shift it by a factor of 1 leftwards, that is u of minus of n plus 1. So this will give me this signal.
Okay, thank you, madam. Great. I think I got clarified.
Okay. So now I think this, how we got this is fine. So I'll look at its stability. I'll recommend you to take some questions from some books of random signals and try to do flipping and shifting operations. It will be very useful when you solve convolution examples, because that is most important thing. Understanding that is most important thing when you solve convolutions. So just look at few examples. So let me
And also one more thing, madam.
yeah.
While doing convolution, sometimes we say x of tau into h of t minus d tau, and sometimes h of tau into x of t minus tau. Which is better? Okay, convolution can be
So
done in
you are
both ways.
saying that when we are having h of tau, x
X
of
of
t
t minus
minus tau,
tau d tau,
and
or
another
x
is x of
of
tau, h of t
h of,
minus tau.
yeah, which one is better?
Okay, so this you can look at your signals, what you're
Okay,
having h of t and what you're having x of t. Now, if suppose I'm having an exponential signal or
okay,
some very random signal, let's say something like this. This is my
okay,
x of t,
okay.
and suppose my h of t is this.
Yes.
This is more handleable.
Okay. So the
So
more simple signal. Yeah,
yeah,
okay.
so the more simpler your signal is, use that signal to flip and shift operations.
Oh, okay.
So when you solve the examples now, you will understand that okay, this signal is very simple. This is more
Oh,
handleable with respect to shifting and flipping. Like if
Okay.
you're having a symmetry in a signal, then it is very easy to handle its flipping operation, because you will get same thing. Or if it is odd symmetry, it will be just flipped around and
Right.
shifted. So
Yeah.
that is when that kind of questions arise now, it is very easy to handle that rather than some
Okay.
very complicated and different signal. So you can
Okay. Okay.
go for this. Yeah.
Okay. The rule of thumb is that whichever signal is simple, okay, use that for t minus tau
Yes,
flipping.
yes. Any signal you can consider, just whichever you feel will simplify your calculations, you can go with it.
Okay. Okay.
Okay. So let's get back to this question and look at its stability. So for that, again, we'll look at summation n running from minus infinity to infinity, mod of 5 power minus n u of minus n minus 1. So this is running from minus infinity to minus 1. So I can write it as n running from minus infinity to minus 1, 5 power minus n. This I can safely replace. So this is actually equal to, I can just replace minus n with m and change the limits accordingly. So this is m running from 1 to infinity 5 power n, and sorry m, and this is an increasing summation, and its common ratio is also, like its ratio is also not 1, like it won't be converging, it is a diverging signal sequence. So basically this will tend to infinity, which means that this system is unstable. Is this okay? Okay. Let us look at the next question. So in previous tutorial we looked at convolution examples for continuous time signals. We didn't look much at discrete time examples. So in this lecture we'll look at some convolution examples for discrete time. And the first example which I am taking is actually very what we can say, a very interesting or very different kind of example, because everything is represented in terms of unit impulse. So to solve this, I won't go with that conventional convolution sum and use that convolution sum to solve this. Actually, that also we can do. But what I'll try to first analyze is this thing. It is, I'll try to understand what do I mean by this. Convolve with unit impulse, shifted unit impulses convolve with each other. Something like this. What do I mean by this? What will I get? So I'll try to first understand this, and then I'll use the properties of convolution to solve this example. So I'm doing this because unit impulse convolution is very important thing. It helps a lot for solving such kind of examples. Okay, so let us first look at this. For this we'll use the conventional method. So let's say this is my x of n and this is my h of n. So here I'll have a summation running from k running from minus infinity to infinity. This x of k I'll have, so this will be x of k minus n naught. And now I want h of n minus k. Right. So I'll replace this n by so basically I'll first flip this signal. I have to flip and then shift. Okay. So I have to first flip. So by flipping, what I'll get, delta of minus n minus n1, or rather more specifically minus k minus n1, and then I have to shift it by a factor of k, by a factor of n. So then this will give me delta of n minus k plus n1. So this I'll have as delta of n minus k plus n1. Now let us play with this. This we can write as delta of minus k minus n minus n1. Sorry, this is minus sign here. And here I'll have plus. I'm just taking negative sign outside. So this I can write as delta k minus n minus n1. This is coming from the fact that delta of n is equal to delta of minus n. So I'm using this fact and getting this expression here. So what I'm having is something like this now. This summation here becomes k running from minus infinity to infinity, delta k minus n naught, delta of k minus n minus n1. Now we know that x of n into delta n minus n naught, let's say x of k into delta of k minus n naught is equal to x of n naught into delta k minus n naught. So I'll treat this term as the shift and this as my x of k. So if I do that, this k will be replaced by this factor, and since it now will be independent, so I'll have it something like this, delta of n minus n1 minus n naught, and summation, this impulse thing will remain as it is, and any impulse का summation from minus infinity to infinity will lead to a value of 1. So this is basically summation delta k minus n minus n1, k running from minus infinity to infinity, and this thing will be equal to 1. So the convolution is again one impulse, but now it is located at n1 plus n0 location. So what I am getting from this is that key takeaway is delta of n minus n naught convolved with delta of n minus n1 is equal to delta of n minus n naught plus n1. So this is what I am getting, and I'll use this fact to solve this question which I am having here. So let me add one page. So here my h of n was, I'll repeat it, was given as 2 times delta n plus 1 plus 2 times delta of n minus 1, and my x of n was delta n plus 2 times delta n minus 1 and minus delta of n minus 3. So now let us try to find out y of n, which is equal to h of n convolved with x of n. So this I can write as 2 times delta n plus 1 plus 2 times delta n minus 1 convolved with delta n plus 2 times delta n minus 1 minus delta of n minus 3. Now I'll use the distribution property of convolution. So this I can write as 2 times delta n plus 1 convolved with delta n plus 2 times delta n minus 1 minus delta n minus 3 plus 2 times of delta n minus 1 convolved with delta n plus 2 times delta n minus 1 minus delta n minus 3. This I can write as 2 times delta n plus 1 convolved with delta n plus 2 times delta n plus 1 into 2, that will be 4. So this is 4 times delta n plus 1 convolved with delta n minus 1 minus 2 times delta n plus 1 convolved with delta n minus 3 plus 2 times delta n minus 1 convolved with delta n plus again 2 into 2 4 4 times delta n minus 1 convolved with delta n minus 1 minus 2 times delta n minus 1 convolved with delta of n minus 3. Now in the previous thing here we have obtained this result. That is, what we have is, if I am having two impulses, delta n minus n naught convolved with delta of n minus n1. So what I'll get is something like this, delta of n minus n naught plus n1. So I'll use the same formula here. I'll use this property to obtain this. So this, if we observed here your n naught is minus 1 and your n1 is 0. So therefore minus 1 plus 0, so that will be equal to minus 1. So again I'll be getting n plus 1 here plus 4 times. Here my n naught is minus 1 and my n1 is equal to 1. So n naught plus n1 is 0. So here I'll be getting delta n. Then minus 2 times, here my n naught is minus 1 and my n1 is 3. So n naught minus 1 plus 3, so it is 2. So this will be equal to delta of n minus 3 minus 1, that is 2. So delta of n minus 2 plus 2 times this factor. Here my n naught is 1 and my n1 is equal to 0. So n naught plus n1 is 1. So this comes out to be n minus 1 plus 4 times. Here my n naught is equal to 1. My n1 is equal to 1. So n naught plus n1 is 2. So I'll be getting delta of n minus 2. And the last factor which I am having here is 2 times delta of n minus, here my n naught is equal to 1 and my n1 is equal to 3. So 3 plus 1 is 4 and therefore I'll getting this factor here. So if I combine the terms, what I am getting is 2 times of delta n plus 1 plus 4 times delta n. Then I'll combine this and this, so it is plus 2 times delta n minus 2 plus 2 times delta n minus 1 minus 2 times delta n minus 4. So this is your output, that is y of n. Any questions at this point?
Madam,
Yeah.
we can also do in another way, no? But graphically, we can plot h1
Yes.
x, then do.
Yes. Actually, I wanted to show this property. This one I wanted to show.
Okay.
In general, if I'm having this now, if I'm having x of n convolved with any shifted version of impulse, then I'll be getting x of n minus n naught.
Yes.
So this property actually helps a lot,
Okay. Okay.
especially when you will do transforms and its properties. This property helps a lot. So I wanted to show this actually, with the help of this unit impulses. Like if you convolve to unit impulse, you'll get another unit impulse. So that I wanted to show, so I took this example. The coming examples will solve graphically. So let us look at another some examples for convolution. So the first one is this. There is x of n is 1 by 2 to the power n minus 2, and h of n is u of n plus 2. So let us first sketch how your x of k will look. So let us look at x of k. This is my k axis. What is it? It is 1 upon 2 power k minus 2, and it is starting from n minus 2. That is, if this is my n hat, that is my n minus 2 is n hat, and this should be equal to this should be greater than or equal to 0, which means this will be non-zero for all n which is greater than or equal to 2. So the signal will be starting from 2 and so on. And here at n equal to 2, or rather k equal to 2, this factor will be taking a value of 1 upon 2 power 2 minus 2, that is 1. So therefore at k equal to 2, this will be taking value as 1. Then at 3 it will be taking value as 1 by 2. At 4 it will be 1 by 4, and so on. So this is your x of k. Now let us try to plot how your h of k will look. So let us try to plot this. That is your h of k. So how will it look? N plus 2 should be greater than or equal to 0. That is, for n greater than or equal to minus 2, it will be non-zero. That is minus 2, minus 1, 0, 1, 2, and so on. So it will be something like this. And so on. So this is your h of n. And now I want to flip this to get h of minus k. So now I'll plot h of minus k. So if I do that, how will it look? So this is going on like this and so on.
So here it is symmetric, right? So
Here it
it's
is not symmetric.
oh yeah, yeah, right,
It
right.
is
Oh,
u
no.
of n. It is
Yeah,
0 here.
yeah, yeah, right, right.
It is not symmetric. But u of n is more handleable compared to this x of k. So if I flip it, whatever was at minus 2 will be now available at 2. So I'll have here 2, minus 1, 0, 0. This is plus 1, this is minus 1, minus 2, and so on. So my h of minus k will be something like this. And this will be 1 for all the values till minus infinity. So this is my h of minus k. So if I consider this factor, that is h of n minus k, this what I am getting is for n equal to 0. So this is the position at for n equal to 0. So for reference, we'll consider this vertical this vertical y axis as an axis that will correspond to my n. So I shift it right or left, it will be like if my n is actually at 0. So if I shift it one step rightwards, n will be at 1, and so on. So this will be our reference axis for n, and this plot which I am getting is for no shift, that is for n equal to 0. Now suppose I have negative shifts, that is if I shift this h of minus k towards this direction, if I shift h of minus k leftwards, will I get any kind of overlap with x of k? No, because it is 0 for all other values here. It is 0. So I won't be getting any overlap for n which is less than 0. less than 0, I won't be getting any overlap. This is n equal to 0, this is n equal to minus 1, this is n equal to minus 2, and so on. So for n less than 0, there is no overlap. Is it okay? But if I shift it this side, then there will be overlap. If I shift it rightwards, there will be overlap. So let us try to sketch what do we mean by h of n minus k. So it's like this. So 0, 1, 2, 3, 4, and so on. Minus 2, sorry, minus 1, minus 2, and so on. And let's say I am having n. I'm having this n somewhere here. That is, here I am having n. Then this is n plus 1, this is n plus 2, and so on. So now I am doing this h of n minus k, and that's why I'll be shifting it rightwards. Now you might be saying that okay, this n is positive, then why we are shifting it rightwards? So actually it's like this. We have flipped it and then we are shifting it, minus of k minus n. So we are shifting it rightwards like this. This is your shifting equation, which actually leads to h of n minus k. So if my n is positive, this quantity is positive, I will be shifting it rightwards. So I am shifting the flipped version of the signal, the flipped version which I had done earlier, rightwards by this operation. So if I do that, this was present, this reference axis was n, this was my n. So this will be located now at n. N was initially at 0. So now it will be located at n. And this factor which was at 2 will now be located at n plus 2. Like this. It will, and then after this it will be 0. That is, from n plus 3 it will be 0. But now here all it will be 1. Like this. And what do we need to know? This x of k, h of n minus k. This we want to know, like how much overlap do we have. So from where to where will be the overlap? Overlap will be from 2. See, the first non-zero value is at 2. So my overlap will start from here. My overlap of this equation, x of k into h of n minus k, will start from here and it will go on till n minus 2. Because after that, this h of n minus k becomes 0. So this is my range of overlap. And therefore, my y of n is given as the range of this overlap, that is from k running from, where is it starting from? 2. K is equal to 2 and it ends at this value, that is n plus 2. That is from 2 to n plus 2. X of k. What is my x of k? It is this factor, that is 1 upon 2 to the power 1 upon 2 to the power k minus 2. And what is the value of h of n minus k for this range? It is equal to 1. So this will be multiplied by 1. And this is arising for my case when my n is greater than or equal to 0. Because my first overlap starts when my n is equal to 0. So this is your equation that you need to solve. So if I simplify this, I'll do the substitution, that is m equal to k minus 2. If I do that, this will be m equal to 0 to n 1 by 2 power m, and this results in 1 minus 1 by 2 to the power, this is from 0 to n, so these are n terms, so it will be n plus 1 terms upon 1 minus 1 by 2. So this comes out to be 2 into 1 minus 1 by 2 to the power n plus 1 for n greater than or equal to 0, and it will be equal to 0 when my n is less than 0. So my y of n, so at this region my y of n will be equal to 0 for n less than 0. So this is the value of my convolution. Any doubts at this point? Okay, so let us look at the next question which I am having here. So if we observe here, this is my x of n and this is my h of n. Now again, if I look at this factor, and let's say this is my n hat equal to minus n minus 1, and this should be greater than or equal to 0. So my for n less than or equal to minus 1, this factor, this u of n will be non-zero. So if I sketch x of k, so if I sketch x of k, this is 0, this is 1, 2, this is minus 1, minus 2, minus 3, and so on. So for n equal to minus 1 and extended till minus infinity, it will be non-zero. And if I'm having n equal to minus 1, this will be taking a value of, so this is 1 upon 3 to power minus n. So if my n is minus 1, this will be 1 upon 1 by 3. So this will be basically 1 by 3. So this is 1 by 3. Then this will be 1 by 3 square. It is 1 by 9. This will be 1 by 3 square, 1 by 3 cube, and so on. So this is my x of k. This is my x of k, and this is my k axis. Now let us look at this u of n minus 1. So how does this look? This is simply a shifted version of your unit impulse, which will be starting from n equal to 1. So this will be like this. And so on. So this is your n, and this is your h of n. Now let us look at h of minus k. That is flipped version of this, like this. Let us look at this h of minus k. So it will basically start from minus 1, minus 2, minus 3, minus 4, and so on. And for all of these values, since I am flipping it, it will be like this. My screen. Yeah, so it will be 1 for all of these values, which are from minus infinity to minus 1, and it will be 0 here. This one is also 0 here. So this is basically my h of n minus k at n equal to 0. So this is my case when my n is located here, that is at 0. My n is equal to 0. Now let us look at two cases. The first case when my n is greater than 0, and the second case when my n is less than 0. So first let us look at the case when my n, so let us look at the case when my n is less than 0. my n is less than 0, so currently my n is here, so it will be this region. So my entire h of k will be basically shifted. It will be shifted leftwards. So it will look something like this. So in this situation, I am plotting h of n minus k. This is 0, this is minus 1, this is minus 2, and let's say this is my n, this is my n minus 1, this is my n minus 2, and so on. This n is now shifted leftwards, and that's why this factor, it was 0 here, it was 0 here, and at minus 1 it was taking a value of 1, so it will be something like this, and so on, and again it will be 0 here. Now let us look at the region of overlap for this condition. So we need to check at x of k into h of n minus k. So if we observe here, my x of k is non-zero from minus infinity to minus 1, but my h of n minus k is non-zero from minus infinity to n minus 1. So my region of overlap is minus infinity to n minus 1 when my n is less than 0. So this I can solve. So for this case, my y of k is equal to summation k running from minus infinity, that is over the region of overlap, k running from minus infinity to n minus 1. In this region, my x of k is 1 by 3 power minus n. So I can just simply write it as 3 power n, and then I can write it as yeah and in this region your h of n minus k takes the value as 1, so this is fine. So this I can write as 3 power, sorry, this is k here, so this I can write as 3 power k plus 3 power k, can write it as 3 power n minus 1 plus 3 power n minus 2, and so on. So this I can write as 3 power n multiplied by 1 by 3 plus 1 by 3 square, and so on. So this is again my infinite geometric progression. So this I can write as 1 by 3. The first term is 1 by 3 upon 1 minus 1 by 3. So this comes out to be 1 by 2 into 3 power n. So this is the value of your y of n. So this is y of n. This is y of n. So my y of n is equal to 1 by 2 into 3 power n when my n is less than 0. So this is the first case that I am getting. Now we'll look at the second case. Okay, so this is what I am having. This is my x of k and this is x of minus k, and the case that I will be looking now is n greater than or equal to 0. So if my n is greater than or equal to 0, that is this region. This region I am shifting rightwards. So what I'll get is something like this. So let's say this is my 0, this is 1, this is 2, and so on, and this is my n, and this is n minus 1. So here I'll be having 0 because at n equal to 0 I was having 0. Then I'll have 1 here, 1 here, 1 here, and this will just continue. till minus infinity like this, and so on. Now if I consider this region x of k into h of n minus k, if I consider this region, this is non-zero from minus infinity to minus 1. This is non-zero from minus infinity to n minus 1, where this n is now greater than minus 1. So my region of overlap is complete thing from minus infinity to minus 1. So my region of overlap is from minus infinity to minus 1. So now I can write y of n is equal to summation k running from minus infinity to minus 1. My x of k takes the value as 3 power k, and my h of n minus 1 takes a value as 1. And therefore I can write this as 1 by 3 plus 1 by 3 square plus 1 by 3 cube and so on, and this comes out to be 1 by 3 upon 1 minus 1 by 3, which comes out to be 1 by 2. So if I combine these two cases, my y of n is equal to 1 by 2 when n is greater than or equal to 0, and it is equal to 1 by 2 into 3 power n when my n is less than 0. So this is the output of your convolution. Any question till this point? Okay, let us look at this question here. So yeah, here I missed to add one thing, and that is here my y of 13, one more information is needed, that is y of 13 is equal to, so what is given is my x of n is equal to 1 for this range, that is 0, 1, 2 till 9, and it is 0 otherwise, and my h of n is equal to 2 for n equal to 0, 1, 2 and so on till n, and we need to find y of n is equal to and we are given that y of n is the output of convolution of x of n and h of n, and y of 4 we are having these values, that is we are having the value of y of 4 as 10, y of 14 as 0, and y of 13 as 2. So let us first sketch these two signals, that is x of n and h of n. So my x of n looks something like this. This is my x of n. It starts from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. This is my n-axis. It is 1 from 0 to 9. Okay, so this is my x of n, and my h of n is something like this. So it is 2. This is 1, this is 2. The diagrams are not to the scale. So it's something like this. H of n is 2 for 0 to n minus, from 0 to n, and we need to find what is the value of n. We need the value of n here. Okay. So first thing that we need, the information that we are having is my y of 14 is 0 and my y of 13 is 2. So what does these two information mean? Let us try to first understand this. So for that, let us sketch this h of minus k. So if I sketch h of minus k, I am flipping it. I am sketching h of minus k like this. So this will be at minus n, This will be minus n plus 1, so on, minus 2, minus 1, 0. I'll be having a magnitude of 2 here, value of 2 here, value of 2 here, value of 2 here, value of 2 here, and so on. But at 1 I'll have 0, 2 also 0, and so on. So this is what I'll be getting when I flip it. Here also for n minus n minus 1 I'll be getting a 0 here. Minus n minus 1, it is 0, and that 0 will continue. So this is what I am getting. Now what information do I have? That y of 13 is 0. That is, currently I am at n equal to 0. Here this is my n equal to 0. And the information that I have is my y of 13 is 0. That is my, when I shift this entire signal, if I shift this entire signal by 13 units, I'll be having a value of 2. That is, when I do that, that is if I shift this, that is I'll need h of 13 minus k. If I do that, then this thing will be at 13, that is this will be at 13, that is here 2, this will be at 12, and so on, and this one will be at 13 minus n, this will be at 13 minus n, and so on, and so on. 13 minus n plus 1, 14 minus n, and so on. So this is what I'll have, and I need to know what is the value of this. Now what I have been given is the value of y of 13 is equal to 2, and if I consider this h of n, if I look at this x of n, it takes the value of 1 everywhere, and this takes the value of 2. So this means that there is only one overlap between x of n and h of n. So basically I am having a situation something like this. I am having a situation which is something like this. So this is 9, 8, 7, and so on. This is my 1, this is my 0, and this is my x of k. So I will be having the value of, that is y of 13 will be equal to 2 only when there is one overlap, which means only this overlap should be there. Which means that 13 minus n should be equal to 9, which means that n is equal to 13 minus 9, which comes out to be 4. So this is the value of n which I am getting. Now we can check this in two ways. The first thing is, in the previous lecture we have seen that if Lx is the length of your signal x, if Ly is the length of your signal y, and if Lh is the length of your signal of your impulse response, then this Ly is Lx plus Lh minus 1. Your Ly is of the value of 14, because your 14th sample is 0, and from 0 till 13 it will be a non-zero thing, because if you flip this h of n, your first sample which is non-zero is located at n equal to 0, and x of n is also non-zero at n equal to 0. So your h of n will be your y of n will be ranging from 0 till its last value, that is it will range from 0 to 13. That is my L of y will be ranging, that is my y of n will be ranging from 0 to 13, which means that this value is 14. Your L of x is given as 0 to 9, which means 10, and this we need to find, and actually this will be equal to n plus 1 because your h of n is non-zero from 0 to n plus 1. So if I do this, 14 is equal to 10 plus n plus 1 minus 1. So my n is equal to 4. Again I am getting the value of n as 4. And second thing that you can do is you can take this value of y of 4, put it in your convolution equation and solve it. We will observe that if only when you are having 5 values of h of n overlapping over the particular region, then and only then you will be getting your value like this. That is, let us try to do that also. Yeah.
Madam, if the question is only find n, what you have suggested, the simple thing, the length of y is equal to length of x plus length of
Yes.
h minus 1 should suffice, right?
Yes, yes.
Okay. And also there is a, we can also use your previous method of analytically expressing as impulse functions and then.
Yes, yes. Anyway, actually, such kind of questions generally appear in competitive exams. So, the simplest thing that you can do is use this formula.
Okay, Lx
Yes.
plus L
This
plus
will
1.
give you answer in no time. And second thing is if my x of n is starting from 0, my h of n is also starting from 0, then if I flip it, flip this h of k, you will observe that your first overlap will be from n equal to 0. So, your output will also start from n equal to 0.
Yes.
And the second thing is if my input is ending at n equal to 9, and if my output is ending at if my impulse response is ending at n equal to 4, so here I have obtained this capital N as 4, my output will be available, the last non-zero value of my output will be available at 9 plus 4, that is 13, and that is what I am getting here.
Okay.
So these are simple tricks which you can use for solving your competitive exam things. But
Okay.
how it is coming, how it is coming from your convolution thing, how it is coming from basics, that I'm trying to explain, so that these things can be better understood when you're just using your formulas.
Okay, madam.
Yeah. Okay, so that was all for convolution, and now we'll look at this thing, that is eigenvalue or transform, or eigenfunction and transform thing. So I am given this impulse response, that is h of n equal to 1 by 2 power n u of n, and I need to find the transform value for this system. So it was seen in the lecture that if your x of n is of the form z power n, then this is basically your eigenfunction for your LTI system. So how it was done, that if I have my output y of n is equal to summation k running from minus infinity to infinity h of k x of n minus k, which is equal to summation k running from minus infinity to infinity h of k. I'll keep it as it is and I'll substitute z power n minus k, which comes out to be z of n summation k running from minus infinity to infinity h of k z power minus k, and this is your transform. And let's say this is h of z. So your h of z is equal to summation k running from minus infinity to infinity. What I am given, h of k as 1 by 2 power k u of k into z power minus k. This u of k is non-zero for k running from 0 to infinity. So I can just simply change this as k running from 0 to infinity 1 by 2 power k into z power minus k. This I can write as summation k running from 0 to infinity 1 upon 2z whole power k. Now this is your infinite geometric progression. Now this will be equal to 1 upon 1 minus 1 by 2z. Yeah, this will be equal to 1 upon 1 minus 2z if mod of 1 upon 2z is less than 1, that is mod of z is greater than 1 by 2, and it will not converge, this series will not converge if this condition is not satisfied. So my h of z is equal to, I can simplify a bit as z upon z minus 1 by 2 when my mod z is greater than 1 by 2. So this is the value of your transform that we are getting. Is this okay? Okay, this transform equation that we are getting here is basically a special transform, and it is Z transform. I think that will start in week 5. After Laplace, that will be covered. So this is a special transform for Z transform. That is Z transform for discrete time signals. So this will be covered in more detail, like what is the use of this condition and other things. Now let us look at the next question. So this is basically based on your differential equation representation for your input-output relation, which is given by this formula. So what was covered in lecture was how we can find the solution of this differential equation. We need to find the value of y of t for this given input and this auxiliary condition, that is y of 0 equal to 1, and any output that we have can be basically written in two forms or components, that is yp of t, which is your particular solution, and second one is yh of t, where this is your homogeneous solution. So now first let us find what is the value of your yp of t, and then we'll find what is the value of your yh of t. Okay, so for finding particular solution, what we do is we assume this yp of t to be very similar but scaled form of this x of t, that is, let's say, k into e power minus 2t, and this is only possible when my t is greater than 0. So this condition is possible when my t is greater than 0, and when my t is less than 0, I don't have any input. So that will be the case which will be covered in your homogeneous thing that we'll look at afterwards. So this is what we are having here, and now let us put this in the given differential equation. So what do we have is 5 into d dt of yp of t, that is k into e power minus 2t, plus 2 into yp of t, that is 2k e power minus 2t, which is equal to 2 into x of t. Your x of t is e power minus 2t u of t, so it is 2 into e power minus 2t. This comes out to be minus 10k e power minus 2t plus 2k e power minus 2t is equal to 2 into e power minus 2t. Yeah, and this we can write, this gets cancelled. This is equal to minus 8, so minus 8k is equal to 2, so my k comes out to be minus 1 by 4. So if I substitute it back here, so my yp of t is equal to k is minus 1 by 4, so this comes out to be minus 1 by 4 e power minus 2t for t greater than 0, so I can just simply write it as ut. So this is my particular solution. Now for homogeneous solution, the differential equation that we need to find is, the solution for the differential equation that we need to find is this. This we need to find. And for this will assume yh of t to be some exponential, scaled exponential. So let's say my yh of t is k tilde e power st. So I'll use this and solve this equation. That is, so what I'll get is 5 into d dt of k tilde e power st plus 2 k tilde e power st is equal to 0. So this comes out to be as 5s k tilde e power st plus 2 k tilde e power st equal to 0. This gets cancelled, and therefore my s comes out to be minus 2 by 5, which means that my yh of t is equal to k tilde e power minus 2 by 5 t. Now I can write y of t this y of t as minus 1 by 4 e power minus 2 t u of t minus, or let's say we are just considering the case when my t is greater than 0, greater than or equal to 0, and we have this plus k tilde e power minus 2 by 5 t. Now still we are having this k tilde constant, and this we can find using this auxiliary equation. That is, I'll have y of 0 is equal to 1 is equal to minus 1 by 4 into 1 plus k tilde, which means that my k tilde is equal to 1 plus 1 by 4, which comes out to be 5 by 4, which implies that my y of t is equal to minus 1 by 4 e power minus 2t plus 5 by 4 into e power minus 2 by 5t, and this is for the case when my t is greater than 0. So if my t is less than 0, then in that case what I'll have is only this homogeneous solution. That is, for t less than 0, my x of t is equal to 0 because it is multiplied by t. So for the case when t is less than 0, what I'll have is only this solution, that is y of t is equal to k tilde e power minus 2 by 5t. Only the homogeneous solution will exist because the entire differential equation reduces to this form. So in that situation, if I try to find this k tilde, so y of 0 is equal to 1 is equal to e power is equal to k tilde into 1. So my k tilde value comes out to be 1, which is equal to, this y of t will be equal to minus 2 by 5 t. This is for the case when my t is less than 0. So I'll just try to combine both of these. So what I had was this condition. So my y of t was equal to minus 1 by 4 minus 1 by 4 e power minus 2t plus 5 by 4 e power minus 2 by 5t for t greater than or equal to 0, and this y of t was equal to e power minus 2 by 5t. And if I combine these, this will always be existing, so I can write it as e power minus 2 by 5t, and this will exist only when my t is greater than or equal to 0. So I can just subtract 1 from this. So if I do that, I'll be remaining with 1 by 4. So I can write this as plus 1 by 4 into e power minus 2 by 5t minus e power minus 2t u of t. So this is my final value of what I am getting, and this thing is known as zi of t, that is zero input signal, and this part is known as yzs of t, which is zero state signal. So this is your final answer. Any questions for this?
Madam, we can find the YT from Laplace also, right? Laplace rule.
Laplace has not been covered yet, but if you go with Laplace, it will be very simple to find it.
Okay.
Yes. I'll take the same question using Laplace in next tutorial and we'll get the same answer.
Okay.
Yeah. But at that
Okay.
time, I'll have to set this y of 0 equal to 0. Then only I can go with it because I need LTI.
LTI means y of 0 is equal to
Yes,
0.
yes. If my initial condition is not 0, I can do it using Laplace, but I'll have some more terms that will correspond to your initial conditions. I can solve it. I'll have some extra terms which will correspond to my initial conditions to get this factor for this.
Okay. Madam, can you explain the significance of a zero input and what is that, zero state? Yeah.
Yeah. So this I'm getting when my x of t is 0.
X of t is 0. Okay.
So when my input is 0, at that time I'm getting my output as this.
Okay. Okay. That is
Yes.
the initial, yeah, 0 at 0. Yeah.
Yes.
The initial signal at t is equal to 0.
Yes.
Yeah.
Yes.
And y of zs is
0
t greater.
state.
Right.
This part is for t greater than or equal to 0. So even if if my input I remove, if I
O-
have some significant input, this will contribute. So based on the state of your input, this will function.
Okay.
Yeah.
Okay. Okay, madam. Thank you.
Okay. So let us look at the next question, and it is, this one is simple one which was similar to one covered in the lecture, but this one gave me some good good sequence or a final thing. I'll rather get a sequence for this. So what I have been given is my y of n is given by this factor here, and I need to find what is my h of n. So I'll find a sequence for this. I'll find a sequence for this, and what I have been given is its initial conditions are 0, which means that I'll get y equal to y of n equal to 0 for n less than or equal to 0. For all of these conditions I'll get it as 0. So for that, let us so basically what I am having is, if I need to find my impulse response, my x of n is equal to del of n if I need to find my impulse response. So this comes out as y of n equal to 2 times y of n minus 1 minus 3 y of n minus 2 plus delta n. Now this, first what I'll do is I'll find at n equal to 0. So y of 0 is equal to 2 times y of minus 1 minus 3 times y of minus 2 plus delta of 0, which is equal to this y of minus 1 and y of minus 2 are 0. Therefore this is equal to delta of 0, and this is my unit impulse. It is like this, and since it is discrete, it takes a value of 1. So my y of 0 is equal to 1. So this is equal to my h of 0 because it's output for an impulse. If I take n equal to 1, then y of 1 is equal to 2 times y of 0 minus 3 times y of minus 1 plus delta of 1. Now this will be equal to 0 because delta n at n equal to 1 is 0. So this comes out to be 2 times y of 0, that is 2 into 1, that is 2. Now if I have n equal to 2, my y of 2 is equal to 2 times y of 1 minus 3 times y of 0 plus delta 2, which comes out to be 2 into 2 minus 3, which is equal to 1. If I take n equal to 3, my y of 3 is equal to 2 times y of 2 minus 3 times y of 1 plus delta of 3, which comes out to be y of 2 is 1, so 2 into 1 minus 3 into 2, that comes out to be minus 4. So my h of n is basically some sequence which is of the form 1, 2, 1, minus 4 and so on, and this one starts from 0. So this is something that we are getting for this given situation. I am taking this example because if you are given some y of n of this form and you have been asked like what is the value of h of n at n equal to 5, then this is the way you should proceed step by step. So for that understanding, I am taking this question because it is again asked in some MCQ format. Then in that case it may not be in some good form like at 2 power n and other things. So for that I am just taking this example. I hope this is clear. If not, please let me know.
Madam,
Yeah.
here the only condition is given is zero initial condition.
Yes.
How did we use that here? Where did we use?
We used it here. One
Uh,
minute. Here.
okay, zero initial means previous values of y minus 1, y minus 2 are zeros.
Yes.
Okay, only y of 0 will be, yeah, okay.
Yes.
Y of 0, yeah, right. So it's, well, okay. Basically, it's a recursively we computed
Yes,
y
yes.
of 0,
It's
y of,
simple recursively we are computing it, but I'm taking this because in some cases you will get some questions where you'll have to find h of 5 or h of 6, and so how to proceed in that case when you're given such a recursive equation. So for that I'm taking this.
okay.
Yeah. Okay. So now the next two questions or the last two questions that I wanted to cover today are based on Laplace transform. So I wanted to take this Laplace transform, and if I'm having a signal x of t, then it will have its corresponding Laplace transform x of s, and this x of s is given as integral from minus infinity to infinity x of t into e power minus st dt. But along with this there is something that is known as ROC, that is region of convergence. So this is your region of convergence, and this region of convergence is basically the region of S in which this integral exists. So that is known as your region of convergence. So in what range? So what is basically your S? Your S is equal to sigma plus j omega. This is a complex quantity. So this S is not a scalar, it is a complex quantity, it is a two-dimensional quantity, and therefore we will be having an S plane. That is, we'll be having sigma, that is real part of S, and we'll be having its imaginary part of S, which is equal to j omega, or let's say j times imaginary part of S, like this, and some region in this S plane. So suppose I have a situation where my Laplace transform is existing in this region only, and these lines are not included, these extremes are not included. If my Laplace transform exists in this region, that is this x of s, this x of s is finite in this region, then this region is known as your region of convergence. Now this your region of convergence will be depending wholly on how your x of t behaves, and only specifying x of s is not sufficient to uniquely recover back your x of t. We need to specify x of s along with ROC, and if I do this, if I specify both of these things, then this x of t, x of s and ROC, these are unique pairs. That is, given x of s and ROC, I can recover back x of t if I know the ROC properly and x of s properly. Then only it will be recoverable. Otherwise, I won't be able to get back because one x of s may correspond to multiple x of t's. Hence, region of convergence is an important concept in Laplace transform. So, whenever you are given any signal x of t and you have been asked to find its Laplace transform, you should not stop by just finding x of s. You have to specify your region of convergence. Laplace transform without your region of convergence will have no meaning. It is very important to specify your region of convergence in your Laplace transform. And this region of convergence is very useful in understanding the behavior of your systems, behavior of your signals, and everything. So this is really an important quantity, and you should know how this has to be found out. So for that, I'll take two examples which will give you some insights regarding your region of convergence. So the first one is very simple example where my x of t is given by this, that is e power minus a t ut plus e power minus bt ut. Now this a and t are some arbitrary constants which I don't know what they are. It may be anything, plus 1 minus 1 plus 2 minus 2, anything. I don't know what they are, and I need to find its x of s. So what we'll do is, based on whatever your value a and b take, we'll try to get some generalized result of how your ROC will look like. So for that, let us first look at this. Let us first try to find what is your x of s. So your x of s is minus infinity to infinity x of t e power minus st dt. This is equal to integral from minus infinity to infinity e power minus a t ut plus e power minus bt u of t e power minus st dt. This I can write as, I can separate the integrals, that is integral minus infinity to infinity e power minus at u of t, or I can also change the limits, that is this u of t will be ranging only from 0 to infinity, so I can just write it like this, into e power minus st dt plus integral from 0 to infinity e power minus bt into e power minus st dt. This is equal to 0 to infinity e power minus s plus a t dt plus integral from 0 to infinity into e power minus s plus b t dt. This is equal to 1 upon minus s plus a into e power minus of s plus a t from 0 to infinity plus e power minus of s plus b t upon minus of s plus b from 0 to infinity. Now let us look at this thing, the numerator of this. So it is equal to e power minus sigma plus j omega plus a into t. Now at t tending to infinity, this will tend to 0 if this will happen if sigma plus a is greater than 0. That is, sigma is greater than minus a. So this will be coming out as 1 upon s plus a when sigma is greater than minus a. Similarly, if we look at this is e power minus sigma plus j omega plus bt. As t tends to infinity, this will tend to 0 if my sigma plus b is greater than 0. That is, sigma is greater than minus b plus 1 upon s plus b, and this will happen if sigma is greater than minus b. Now let us consider that your a and b are not same. Your a and b are not same, then in that case the entire Laplace transform, your entire Laplace transform, that is this x of s, will converge only when these two things are simultaneously converging. That is, your sigma should be greater than minus a and your sigma should be greater than minus b. That is, your sigma should be greater than max of minus a minus b. This is the situation, this is your region of convergence that you are getting. So let us try to plot it. So what we are getting is x of s is equal to 1 upon s plus a plus 1 upon s plus b, where your sigma is greater than max of minus a minus b. Okay, so case 1, your a is greater than b, which means that your minus a is less than minus b. So this is the situation that you are having. So this is your minus a and this is your minus b. Your minus a is less than minus b, and if I consider ANDing thing, then my region of convergence is like this. This is your sigma, this is your j omega. Now if you observe, this x of s will take a value of infinity, but it will tend to infinity when my s is equal to minus a and when my s is equal to minus b. At this, my x of s will tend to infinity, and these are known as poles. These are known as poles of Laplace transform, poles of the Laplace transform of this, and these are represented using a cross sign like this. So these are your two poles which correspond to this Laplace transform. Now if we look at the second condition, that is case 2, where my a is less than b, which implies that my minus a is greater than minus b. I'll have it something like this. Let's say my minus a lies here, my minus b lies here. It can be anywhere over your sigma axis. I'm just taking arbitrarily j omega, and it will be something like this. This is your region of convergence, and again I'll have two poles which are something like this. That is at s equal to minus a and s equal to minus b. Any questions at this point?
Uh, Here, the poles are not included, right? It
Poles are
is
never included in ROC.
exactly greater than minus
Yes,
b.
yes. Poles are never included in ROC. Zeros are, poles are never included. Let us look at the next question. This is somewhat more interesting one than previous one. This will give you more insights about your region of convergence. So now here what I have been given is this signal, that is my x of t is equal to e power minus at minus e power minus bt u of minus t. So let us first try to find out what is your x of s, which is equal to integral from minus infinity to infinity. Your x of t is e power minus at u of t minus e power minus bt u of minus t into e power minus st dt. Now I'll just separate out these integrals, that is from minus infinity to infinity, or rather I'll also make use of this unit step function here. So this thing will make it run from 0 to infinity. So therefore I'll have it as 0 to infinity. I can remove unit step into e power minus st dt, and minus I have this. Now this thing here, u of minus t, is ranging from minus infinity to 0. So it is minus infinity to 0 e power minus bt into e power minus st dt. Now we have solved this in the previous question. We have seen this here. The same integral which results in 1 upon s plus a when my sigma is greater than a. So this is equal to 1 upon s plus a, and this exists only when my sigma is greater than minus a. Now let us look at this thing. Let us look at this thing here. So this is minus of integral from minus infinity to 0 e power minus s plus b t dt. Now this I can write as 1 upon s plus b into e power minus of s plus b t from minus infinity to 0. Now at minus infinity, at t tending to minus infinity, that is at t tending to minus infinity, this s plus b, that is sigma plus j omega plus b, this value should be, this sigma plus b should be less than 0. In that case only, in that situation only, at t equal to minus infinity, e power minus s plus b t will tend to 0. So in that situation, the region of convergence for this factor will be sigma less than minus b.
Madam, in fact, both are similar, right? Earlier, it should be same.
No,
Sigma less than minus p, like the previous one.
see, here you are having u of t. Your region of convergence is coming as sigma greater than minus b.
Okay.
But here it is u of minus t. It is ranging from minus infinity to 0.
Oh, u of minus t. Okay,
Yes.
okay.
So this comes out to be 1 upon s plus b, and this will exist only when my sigma is less than minus b. Now you observe carefully your x of s here and the x of s which you are getting here, they both are identical. But what is making a clear distinction in both of them, like what is making them different, is your region of convergence. Here your region of convergence was sigma greater than max of minus a comma minus b. Here your region of convergence is something like this. Now let us look at how exactly we are getting this region of convergence. So what we are having is x of s is equal to 1 upon s plus a plus 1 upon s plus b, and my region of convergence is sigma greater than minus a and sigma less than minus b. Now let us look at both the cases. So the case 1 is my a is less than b, which means that minus a is greater than minus b. And note that these two conditions should be simultaneously satisfied. It is an and condition, and it is intersection and not union. So here what we are getting is your minus a is here, your minus b is here. That is, your minus a is greater than your minus b. What the first condition says, that your sigma should be greater than minus a. That is this region. This is your sigma, this is your j omega. And your second condition says that your sigma should be less than minus b. It should be less than minus b, that is this region. There is no overlap. there is no value of sigma that will simultaneously satisfy these equations. So in this situation, the Laplace transform is not existing. At this situation, we are having no overlap, which means that Laplace transform doesn't exist. Because in this region, in both of these regions, like if I consider this region, if I consider this region, here 1 upon s plus b will tend to infinity. This will tend to infinity, or rather your for integral which was corresponding to this one, minus infinity to 0 e power minus bt dt into e power minus st, this will tend to infinity. If I consider this region, in this here 0 to infinity e power minus at e power minus st dt, this will tend to infinity. Means it won't converge to a finite value in any of these two regions. There is no overlap, there is no sigma that will simultaneously satisfy both of these conditions, and therefore your Laplace transform won't exist. Now let us look at the second case. The second case is your a is greater than b, which means that your minus a is less than minus b. So it's something like this: sigma j omega. This is your minus a, this is your minus b. So your first condition says that your sigma should be greater than minus a, that is this region. And the second condition says that your sigma should be less than minus b, that is this region. Now if we observe carefully, this is the region of your overlap. This is the region of your overlap. That is, in this range of sigma, both of your integrals will converge to a finite value, that is, you will get this value. And therefore your ROC in this case will be minus a less than sigma less than minus b. So this will be a region of convergence. Is this okay? So you have to be very careful while finding your region of convergence. All the terms should converge. There should that in the region of convergence, all the terms should converge.
Madam, in some textbooks I saw they use mod of yeah, no, real value of yes
See,
is between a and b. That should
yes,
that
yes, yes.
maybe they are generalizing actually the one.
S is your sigma plus j omega. So your sigma is real part of S.
Okay,
So
so
you can just write this as minus a less than real part of S is less than minus b. No harm.
okay,
Yeah, it is same thing.
okay. Okay, so so without even graphing, from the conditions of 1 by s plus a and 1 by s plus b, we can straight away make that minus a less than sigma less than minus b, right?
No, no, no. Actually, I didn't give any specific condition on A and B here. But in general, the questions that you will get will have some finite values, like some values given. It will be something like this: minus 2t u of t minus e power minus 3t u of t.
Okay,
Something like this will be given.
okay,
So based on the values that you are having here, you will get the value of your Laplace transform and your region of convergence. Or at least you will be given some conditions like your a is greater than 0, a is greater than b, or b is greater than a, and accordingly you can find the region of convergence. But in this example, I wanted to show that it may happen that you are not getting any overlap. In that situation, your Laplace won't be existing.
Okay. So that means, whatever may be the value of B, the convergence only happens in the case when A is greater than B.
Yes.
Right. Okay.
And like previous example also, here we are having poles at s equal to minus a and s equal to minus b. So I'll just mark it with a cross here. This was all I had planned to cover today. So if you have any doubt in any of the questions, please let me know. Else you're free to leave the meeting.
Thank you very much, madam. So I got several doubts cleared. Thank you.
Thank you.